Okay, so in this video we will talk about a very interesting puzzle in quantum mechanics called the EPR paradox. EPR standing for Einstein, Podolsky and Rosen. So quantum theory itself was a breakthrough discovery in physics. But Einstein, one of the inventors of quantum mechanics, neither really liked or believed in quantum mechanics that Niels Bohr and himself devised. So in reaction to the uncertainty principle in quantum mechanics, Einstein didn't really believe in the uncertainty principle, and he even said God does not play dice, meaning that the universe is determined by well-determined physical laws. So Einstein, as an opposer to the uncertainty principle, he believed that the principle of the universe relied on well-determined, well-defined physical laws. So he said, well, God does not play dice. But of course, Einstein's conception of God wasn't transcendental. He rather regarded God as the natural force behind the principles of the universe. So to undermine the quantum theory, Einstein, Podolsky and Rosen presented a thought experiment that was claimed to conflict with the principles of quantum mechanics. So the paradox can be described in the following manner. So suppose that we're given a Bell state, okay? 1 over square root 2, 0, 0, plus 1 over square root 2, 1, 1. And suppose that we want to measure this state in the sign basis. So we want to know the probability of seeing state ket 1 when measuring the first qubit, and if we measure, if we see a plus, then we want to know the probability of seeing plus in the second qubit. So to make a measurement on the sign basis, we need to write this state in the measurement basis, in the sign basis. Okay, and as a matter of fact, the Bell state in the sign basis is again a Bell state. So the claim is that we claim that this Bell state is equivalent to another Bell state in the sign basis. So this is equal to 1 over square root 2 plus 1 over square root 2 minus minus. Okay, so to see this, let's write the right hand side as, so this is equal to, so we're writing here as 1 over square root 2. So we're writing plus in the canonical basis. So this is 1 over square root 2, 0 plus 1 over square root 2, 1. Okay, and plus, now I'm writing this part. So we have minus 1 over square root 2, 1, tensor 1 over square root 2, 0, minus 1 over square root 2, 1. Okay, so then distributing this is equal to 1 over square root 2, 1 over 2, 0, 0, plus 1 over 2, 0, 1, plus 1 over 2, 1, 0, plus 1 over 2, 1, 1, plus 1 over 2, 0, 0, minus 1 over 2, 0, 1, minus 1 over 2, 1, 0, plus 1 over 2, 1, 1. Okay, and these terms cancel each other, and we are left with 1 over square root 2, 0, 0, plus 1 over square root 2, 1, 1. So we just show that this Bell state in the sign base is equal to the Bell state in the canonical basis. Okay, so then the probability we see plus in the first qubit is simply 1 over 2. Okay, and if we see plus in the first qubit, the new state of the system will be plus plus, right? Because minus minus is inconsistent with our measurements, so it can't be that. But our new state will be plus plus. Now, the probability of seeing plus in the second qubit after measuring the first qubit is exactly 1, because they're entangled, right? So the Bell state is entangled. So the EPR paradox says that unlike Heisenberg's uncertainty principle, we may actually know the bit value and the sign value of the first qubit simultaneously. What we do is that we prepare an entangled state, okay? So we prepare a Bell state, okay? And what we do is that we keep the first qubit on Earth, and we move the second qubit to, say, to a distant galaxy or to a distant planet. And next we measure the first qubit in the standard canonical basis. So, okay, so we keep the first qubit on Earth and take the second qubit to a distant planet. Okay, so first we measure the first qubit in the standard canonical basis. In the 0-1 basis, okay? Okay, so, and simultaneously we measure the second qubit in the sign basis. In a plus-minus basis. So these qubits are physically separated from each other, okay, and light cannot travel from the second qubit to the first qubit. So measuring the second qubit will not disturb the state of the first qubit. And upon measuring the second qubit, we get the sign value. And measuring the first qubit, we get the bit value. But this contradicts Heisenberg's uncertainty principle, because Heisenberg's uncertainty principle tells us that we cannot know two distinct quantities about a quantum system or about a qubit. So we have a paradoxical situation here. So how do we solve this problem? And the way quantum mechanics explains this paradox is that when we measure the first qubit, as soon as we measure it, the state will not be entangled anymore. Because if we measure the first qubit as 0, say, okay, so if we measure the first qubit in the canonical basis and say the outcome is 0, the new state will be 0, 0. So as soon as we make a measurement in the canonical basis, whatever the outcome is, either 0 or 1, the outcome will be, the new state will be a non-entangled state. It will be a decomposable state. It's either going to be 0, 0 or 1, 1. If it's 0, 0, and the same argument is valid for 1, 1, well, this state is not entangled. This is simply the tensor product of two single qubit systems, right? So, in fact, there's a really nice property about Bell states. Given any orthonormal basis states, okay, let's call them U and U perp. The Bell state, 1 over square root 2, 0, 0, plus 1 over square root 2, 1, 1 state in the canonical basis, well, sorry, in the UU perp basis, is still a Bell state. So not only is this valid for the sign basis, but it's valid for any given orthonormal basis states. So this is called the rotational invariance property. Rotational invariance property. So the Bell state is equivalent to another Bell state in the UU perp basis. Right, so this is equal to 1 over square root 2 UU plus 1 over square root 2 U perp U perp. Okay, so suppose that this represents the canonical basis 1, 0, and assume that we have U perp. Suppose we have another orthonormal basis states, V and V perp, and assume that the angle between V and U is theta. Similarly, the angle between V perp and U perp is theta. Okay. Now suppose that we want to measure the first qubit in the UU perp basis, and then assume that we want to measure the second qubit in a different orthonormal basis state, say in the VV perp basis. Okay. Now the outcome, if the outcome of the first qubit, we measure the first qubit in the UU perp basis, if the outcome of the first qubit is U, then the new state of the system will either be, so it's going to be UU, okay? If we measure the first qubit in the UU perp basis, the outcome will either be UU or U perp U perp. But let's suppose that the first qubit is observed as U. And in that case, the outcome will be UU. So now if we measure the second qubit, if the new state of the system is UU, and if we want to measure the second qubit in the VV perp basis this time, now the probability of seeing V is simply the square of the inner product of U and V, which is cosine squared theta. The probability of seeing V in the second qubit is cosine squared theta, right? And similarly, if the outcome of measuring the first qubit was U-perp, then the new state would be U-perp, U-perp. And if we measure the second qubit in the VV-perp basis, the probability of seeing V-perp is again cosine squared theta. So the probability of seeing orthogonal complements is preserved through when we're working with entangled Bell states. So this is the EPR paradox in quantum computing. But we will not delve into details. From now on, we'll be more concerned with the computational aspects of quantum mechanics. Okay? So in the next lecture, we will look at classical and quantum gates. So I'll see you in the next video.